Last time on Mastering AMC 1012, we covered all of these combinatorial identities, and we saw how it almost trivialized these two examples over here. But today, we're going to see how to use combinatorics in everyone's favorite subject, geometry situations. But it's actually nothing to do with geometry, so don't worry. The general formula for the number of rectangles of all sizes in a rectangular grid of size m by n is m plus 1 choose 2 times n plus 1 choose 2. Now, why is this true? It's true because how do we form a rectangle, first of all? We form a rectangle by choosing two lines. Let me draw it out so you can understand. Basically, let's say we choose two lines, two vertical lines, and then we choose two horizontal lines. And there we go. We have a rectangle right here, right in the center region over there. Two vertical lines, two horizontal lines forms a rectangle. And you know what's cool is that for any combination of two vertical lines we pick, no matter what they are, and any two vertical lines, it doesn't matter what they are, they will always form a rectangle on the inside. So to count the number of rectangles, we just count the number of ways to pick two vertical lines and the number of ways to pick two horizontal lines. Well, how many ways to pick two vertical lines? Well, it's m by n, so there's n. This is because this is n. There's n plus 1 of these lines. In this case, n is 4, so there's 5 lines like this, 5 horizontal lines. And from them, we just choose 2 of them. 5 choose 2 equal to 10. So 10 choices for 2 horizontal lines. Now what about vertical lines? Well, again, in this case, it does not necessarily have to be a square grid, but because it's m, there's going to be m plus 1 of these vertical lines. So m plus 1, choose 2 vertical lines. In this case, it's again 5, but m and n do not have to be the same. M equals 10. So the number of rectangles in this grid, 10 times 10, 100. And that is it. That is a very powerful formula that we will be using in this problem. Not in this problem, but in one of the other problems. In this problem, we have a 5 by 5 grid, and it contains a collection of squares with all sizes, 1 to 1 and 5 to 5 to 5. So 2 by 2 squares, 3 by 3 squares, 4 by 4 squares, and 5 by 5 squares. And how many squares contain the black center one? Let's start one by one. There really is only one square, 1 by 1 square containing the black center square. That's simply 1. What about 2 by 2 squares? Let's see. There's this one over here. There's also this one over here. There's this one over here. And there's this one over here. There's 4. Now, we can keep going on counting, but let's see something a little bit smarter. How many choices do we have for which 2 squares okay, let me explain that. How many horizontal ways do we have to choose which 2 of these unit squares will be covered by a horizontally? So for example, what I mean is, in this case, we could have a 2 by 2 square that covers like that or like that. They both cover 2 unit squares horizontally. We have 2 choices. Let me draw them out. This one over here, this one over here. What about vertically? Well, vertically, 2 choices again. We've got this one over here and this one over here. Okay, well, we've got, and notice that for each choice of vertical 2 squares to span upon for our side length of one of the squares we're actually counting, so it spans over 2 unit squares, I should say. This one and this one form a square. This one and this one form a square. Similarly, and let me just complete the square. It's going to be like that. This one and this one form a square, like I mentioned earlier. And then if you choose the left, these two squares to be your horizontal unit squares to span upon, it will be these two squares and this one. So as you can see here, there are two choices for where the x coordinates of the squares can be, and two choices for the y coordinates. So essentially, it's just 2 squared as well. 4 or 2 squared. Now, what about 3 by 3 squares? This is where it gets interesting. Now, we could count them, but let's use our smart logic again. For the x coordinate, you could have something like this. You could have something like this. Let me use a different color. You can have something like this right here. Or even something at the bottom right here. Okay. That means for the y coordinate over here, it can be this. The y coordinates could have 3 choices, as you can see. What about the x coordinates, or the horizontal unit squares it spans upon? X coordinates, just this one over here, this one over here, and over here on the right side. Got 3 choices. It can be the left 3 squares, the middle, or the right 3. So 3 choices for where it can be vertically, 3 choices for where it can be horizontally, and each combination will form a 3 by 3 square that contains this black center unit square. Because all the y coordinates contain this here, and all the x coordinates contain this here. Isn't that cool how we can just take all possibilities now? Each y and x value will form a square. Just 3 squared. From a 3 by 3 square. Now what about 4 by 4 squares? Again, we can manually count it, or we can see that it can span over these 4 squares. The y values can be these 4 squares, or these 4. 2 choices. And the x values can be these 4, or these 4 squares. 2 choices again, plus 2 squared. Finally, 5 by 5. 1 choice, just 1. Or by our same logic again, if you want to practice a little bit more, 1 choice for the y values, 1 choice for the x values, so 1 squared. And you can make that a square as well. Now we just add up a bunch of squares, not these squares, these squares. So let's do this. 1 plus 4 plus 9 plus 4 plus 1 equals 19. Because this is 5, this is 5, this is 9. 19, the final answer, and that's how you solve this. And I know this problem was interesting, but we're about to solve an even more interesting problem. It's a similar problem, except now, how many rectangles formed by the grid lines contain the black center square? Remember our rectangles formula earlier? Well, sadly, that won't work, because now we have a condition involved. But the good news is we can modify it a little bit to count this. First of all, you know how we had our 2-line logic, 2 vertical lines, 2 horizontal lines? Can we maybe use that a little bit? What are our possibilities for 2 vertical lines? Let's just explore a little bit for now. If our 2 vertical lines are these 2 lines, well, the rectangle will very clearly encapsulate the square. What if it's something like this? That will also include the square, or something like this. That will include the square. What about something like this? Oh no, that won't include the square. So it seems like 1 vertical line has to be the left of the black square, and 1 has to be to the right? Let's verify this. Let's see if this is actually correct. So if 1 vertical line is to the left and 1 is to the right, then the black square is contained within the values inside. So this does work. But if they're both on one side, so let's say they're both on the right side. Uh-oh. There's no way the black square can be inside anymore. So yes, it is indeed true. You might have to choose a vertical line on the right side and one on the left side. How many ways are there? Well, 1, 2, 3 choices for the right vertical line. And then 1, 2, 3 choices for the left vertical line. So 3 times 3 equals 9 choices for vertical lines. Horizontal lines? Let's count them now. It will be very similar, as you can probably guess. 3 choices for the top horizontal lines and 3 choices for the bottom horizontal lines. Again, there has to be one horizontal line below the square and one above. And then that will always have the black square in the middle. So as long as we choose 2 horizontal lines that the black squares are in between and 2 vertical lines that the black squares are in between, it should work, right? Let's take an example just to make sure. For example, if we have something like this, the vertical lines, check. Now, what about horizontal lines? Something like this, let's say. It looks like the rectangle contains the square, so we're good. In this case, we see both horizontal lines and vertical lines outside the black square. Okay. What if just one of them are true? What if it's in between the vertical lines, but then the horizontal lines are like this? Uh-oh. Nope, it's not inside. So for it to be true, both the vertical lines have to be around the black square and the horizontal lines. Got 9 choices for the vertical lines and 9 choices for the horizontal lines. 9 times 9, 81 is the answer. And that was a clever application of the rectangle counting technique. Okay, next off, we've got a problem from the AMC 10. As shown in the figure below, a regular dodecahedron. And this is a polygon that has 12 pentagon faces. Floats in space with 2 horizontal faces. What is the problem referring to? It's referring to these faces over here. And I know you can't see it, but it's this face over here that's kind of bounded a little bit by. Let me do my best attempt to draw it. This kind of here. If you can imagine that something is at the bottom of this whole diagram you see here, that would be that bottom vertical thing it's talking about. And they're basically saying those 2 are horizontal, so they're both going to be parallel. And now what they're saying is that there's 5 slanted faces adjacent to the top face. 1, 2, 3, and then there's 1 here you can't see, and 1 here you can't see. And then there's 1, 2, and you can't see the other 3, but there's 3 behind right there. So 5 in the first ring, 5 in the second ring, 1 on top and 1 on bottom. So we're asked to find how many ways to move from the top to the bottom face by just going on adjacent faces. You can't just jump wherever you'd like. And we're not allowed to visit a face more than once, at most once. And moves are not permitted from the bottom ring to the top ring. What it's saying is that once you go down, let me erase this. Once you are here, you go down, you can't just come back up. So you have to be going closer to the end goal, which is the bottom. Let's count this. Let's take it one step at a time. First of all, he starts at the top, right? He starts at the top. So how many choices for him to move down? There's 1 choice, 2 choice, 3 choice, and there's 5 in the ring, so 4 and 5. So as you can see, 5 choices to go from the top to the first ring. Okay, now we're at this ring. What can we do? What are our options here? Let's take a look. Well, if you're lazy and you want to get there fast, you can just go directly down. But we don't have to go down right away. We can roam on this first string a little bit and then go down. So it's going to get a little bit tricky with casework if we try to approach it like that. So let's instead see how many ways are there to do anything on the top ring before moving to the bottom ring. Just anything. You can do nothing and just stay there, or move around right, move around left, whatever. But the key thing to remember here is that you're not allowed to go to a face that you've already visited. You've only visited once. Okay, let's count this. So this is a very symmetric problem. It's symmetric about all 5 faces. So let's just say you go down to this one. They're all symmetric, so it doesn't really matter. Anyways, you multiply by 5 for all. So if you move down to this square over here, this pentagon over here, not square, I got confused with the previous problem. Then we can go right or left, or we can stay there. So one way is you just stay there. We don't do anything on this face. We're directly anxious to get to the next ring. Or we can roam around a little bit. What if we move right? Let's say we move right. Can we go back left? Nope, because this face is already visited, and we can't go back to a visited face. So at that point you can stop, or you can go right again, maybe. You go right 2 times. At that point you can stop again, or you can go right again. But this time in our perspective it would look like left, because we'd be going here. And then again you can stop and be ready to go down, or go right again. And then finally you come back. Or I should have probably said counterclockwise instead of right and left. Okay, so we essentially have 4 choices if we're going right. Go right 1, go right 2, go right 3, and go right 4. But once we reach go right 4, we can't go right a 5th time because we've already visited this face. And the same reason why we can't ever turn back, because we're going to go back to a visited face. So we essentially have 4 choices here if you want to move right. Now what about, or counterclockwise? What if you wanted to move clockwise, or left from this direction? You can go here, 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 here. It's actually a very similar as the right case. It's literally the exact same. It's symmetric. You can go left 1 before stopping, left 2, left 3, left 4. And you can't go left the 5th time, or you end up back where you started, but you can only visit each face at most once. So plus 4. So essentially we have total 9 ways here. 1, don't move at all. 4, move counterclockwise somewhere. 4, move clockwise somewhere. 9 choices. And now we're finally ready to move down to the bottom ring. Okay, so how many choices to move to the bottom ring? Let's just say we ended up here. Again, they're all symmetric. It doesn't really matter. But if we were here, how many choices do we have? We can go here or here. Only adjacent faces. So there's just 2 choices. Okay, now what happens if we land back here? Now, once we're at the bottom ring, if you're in a rush, you can just go straight down to the bottom. But you can also move a little bit, just like we could in the first ring. We can either just not do anything on the second ring. We can move 1 choice. We can move right 1, right 2, right 3, right 4. 4 choices. Left 1, left 2, left 3, left 4. 4 choices. Notice that it's exactly the same as the top ring. Isn't that cool? Because the reason is it's the same ring essentially. You cannot go more than 4 right before you end up back at the same spot. You can't go more than 4 left. And you can stop whenever you'd like, after 2 left maybe. Or you can just stay there and not move at all on the second ring. That's a total of 9 choices. So that's it. And after that, finally, you've only got one choice to reach the bottom. You just go to the bottom. One choice. Let's finally multiply this up. 5 times 9 times 2 times 9 times 1 equals 810. And that is our answer. Next, we're moving on to geometric probability. And geometric probability is dealing with an infinite possibilities by using geometry again. Yes, we're going back to geometry. But we'll do that in the next video over here.